Okay, last type of free response questions that we're going to go over here. They're differential equations. They're always calculator inactive, and there's always one on the final exam. Now, they don't always ask you the same thing, but you will find a very common thread. So obviously, if you look at the problems here, we've got the first one here is from 2014. We got one in 2013, 2012, 2011, 2010. I mean, it's every year. I don't have the most recent ones on there, but I did want to show you in 2015. Question number 4 was a differential equation. This one you had to actually sketch the slope field for a few points, find the second derivative. Particular solution comes into play. 2016, again, question number 4, differential equation, slope field at those 6 points. They ask you for a tangent line and an approximation, and then the final part they ask you for the particular solution. 2017, last year, looks a little different in 2017. This is the potato problem. If you heard anything about that or saw anything about it on Twitter after the exam, everybody was freaking out over the potato problem. But look, it's just a differential equation, and they ask you the same sort of questions. They just don't ask you to do the slope field part. Equation of a tangent line, second derivative. They give you another model. And they ask you to solve that one. So, I mean, it's question number 4. Again, I didn't look at the specific question numbers of these, but it tends to be question number 4. It's always calculator inactive. First 2 are calculator active. The second 4 are calculator inactive, and the differential equation tends to be question number 4. We will hopefully go over the 15, 16, and 17 as kind of review here in the next couple of weeks, but let's look at the ones that I have in the packet that you're looking at. So we've got a differential equation, dy over dx is equal to 3 minus y times the cosine of x. Let y equals f of x be the particular solution in the differential equation with the initial condition f of 0 equals 1. Remember, anytime you see that initial condition, you're probably going to use that at some point in time. Something before we even get into the problem that I want to note, look at your differential equation. It has y and it has x. So at some point in time, you're probably going to end up having to separate variables, possibly. I don't know what this question is going to ask, but that's something to keep in the back of your mind. When x and y are blended, you may have to separate them. So let's look at, and this may be important. The function f is defined for all real numbers. May be important, may not be important, but we'll see. Let's look at part A. A portion of the slope field of the differential equation is given below. Sketch the solution curve through the point 0, 1. Now, usually they're just asking you to do the slope field at certain points, but sometimes they do ask this type of question. So let's review how to do it. I showed you how to do it when we learned differential equations, but let's review it. So the key is you start at 0, 1. You've got to have that point right there. That's a definite. Okay, the rest, you got a little leeway, okay? But here's what we do. We start with that point. I always go to the right first. Most people tend to go to the right first, so let's do that. We're going to follow the slope of that tangent line right there. Okay, so I'm going to kind of try and keep its slope, and then I'm going to follow the slope of these lines. So it's becoming less and less positive slope, and then we kind of hit this maximum point right here, and our tangent lines start curving down, and then it becomes more and more steep. Okay, so kind of following the curves right there. That's kind of the part that we're looking at here on the right. When we look at the left, kind of compare their slopes here. These slopes get a little bit steeper, over here on the left. So if we follow the slope of this tangent line, it was going about like this. So if we kind of follow that right here, we run into this steeper slope and this steeper slope. So we should be decreasing a little bit faster than we were on the right side. And then I start running into, I'm going to make a turn about right here. And then we start increasing pretty, not super rapidly right here, but we do start increasing with these slopes. I know this is a pretty rough sketch here. I'm trying to do this with a tablet, so it's not the easiest thing ever. But you kind of just follow the slopes there. Now, let's be real. You get 1 point for this, okay? So I feel like I've never been a reader. I want to be at some point in time, and I haven't been. I feel like they would be kind of lenient with this. I mean, if you get the general idea that you got to increase here, but you don't want to increase too much because these slopes aren't super steep, and that the left side should definitely have more dip in it than the right side because of the difference in the slopes there. I think you're gonna be okay. And you definitely have to go through that initial condition at 0, 1. That's a non-negotiable. I do know that much. So don't stress over something like that, just like you shouldn't stress over when they make you plot the slope field. Usually it's like 2 points, maybe 3 points, if they give you a slope field. So, don't stress over that part. Focus more on the other parts, the calculation parts. So let's look at part B. Part B says, write an equation for the line tangent to the solution curve in part A at the point 0, 1. Use the equation to approximate f of 0.02. So let's do that. Write the equation for the line tangent. We need the slope. Slope comes from the derivative. The derivative was given to us, dy over dx. They gave that to us. So dy over dx is equal to 3 minus our y value, 1, times the cosine of our x value, 0. So 3 minus 1 is 2. The cosine of 0 is 1. So 2 times 1 is 2. So that's the slope of the tangent line. So our equation would be y minus the y is equal to the slope times x minus the x. Now, technically you can leave it like that. I don't like leaving an x minus 0, so I'm just going to drop that part. And there's the equation of our tangent line. And really, this one's not that bad if you want to go ahead and put it in slope-intercept form. But again, just remember, be very careful when doing stuff like that. If you keep writing, they keep grading. So be careful about simplifying too much. You get 1 point for your tangent line equation, but notice that's not all they were asking for. Use the equation to approximate f of 0.02. So f of 0.2 is equal to 2 times 0.2 plus 1. So 2 times 0.2 is 0.4 plus 1 is 1.4. Okay, so you get 1 point for the tangent line equation. You get 1 point for the approximation. So we got 3 points so far. So that must mean that this last part, and it usually is, with these differential equations, they typically, not always, but typically ask you to find a particular solution. And usually that's going to be worth 5, 6 points. In this case, it's worth 6 because we've only had 3 so far. So it just kind of depends. All right. So I mentioned before, when we looked at that differential equation that they gave us, you should notice that it had a mix of y and x. So we need to begin by separating those variables. You've got to get the y with the y and the x, the y with the dy and the x with the dx. Notice when you look at the rubric, they'll always put this on these differential equations when they ask you to find the particular solution. it says you get 0 out of 6 points if you don't separate the variables. So it doesn't even matter if like from that point you kind of start doing things right. If you don't get step 1, separating the variables, if you don't get that right, then you're done. Okay. So I typically do this in one step. My dx obviously is going to come over here. You really don't need to draw the arrow. I'm just pointing it out to you here in these notes. So it was in the denominator, so we multiply. So we get cosine of x dx here on the right side. On the left side, this has got to go over here, but it was in the numerator because we didn't have a denominator over there. So the only way to move it over there is to move it by division. Okay. Separation of variables is never going to be, I repeat, never going to be by addition or subtraction. The only way to move things when it comes to differential equations is to either multiply by them or divide by them. Okay. So let's start with our integration. So there's our separation of variables. 1 point for that step right there. Then we need to take the antiderivative of both sides. So we've got an expression in the denominator, so that means it's going to be a natural log. And when we do the natural log, remember we need the absolute value. It was negative y, so we need to stick a negative in front of that expression right there. The antiderivative of cosine is sine. Now, typically, just like when we were learning about differential equations, I typically always put the plus c on the side with the x, and that's typically what they do on the exam as well, on the rubric. So you can put it over there, but it's just easier because eventually, what are we going to do? We're going to end up solving for y. So why put something on the side with y when we have the choice and we could just go ahead and put it on the other side? You get 2 points for your antiderivative. So 1 point for your y antiderivative, 1 point for your x antiderivative. So we've already got 3 out of our 6 points. We've already got half of it. So even if we don't make it any further, we've got this much. Okay, so we've taken the antiderivative. We need to find our particular solution. So we need to use our initial condition. Our initial condition was f of 0 equals 1. So let's plug in 1 for y and 0 for x. And let's see what happens. Well, the sine of 0 is 0. So we've got negative natural log of 2. At this point, we can drop the absolute value because 3 minus 1 is 2, is equal to our c. So you get 1 point for, I forgot. You get 1 point for the constant of integration. So putting your plus c on there. And then you get 1 point for using the initial condition. So now we've got to go back up to this line right here. And we've got to solve for y. So let's plug in our c minus the natural log of 2. I like to go up beside it. I mean, you should have enough room on your exam because solving this should be a linear process. So you should have enough room to go over here to the right side. I just like to go back to this line because I can just copy it and then I change the c to whatever c value that I found. Okay, so first things first, we got to get rid of this negative. So that means we need to change the signs of everything. Now, they always give an explanation for why you can drop the absolute value bars, but I've never seen it be a problem. So I just drop them, okay? So when I change the signs of everything, I'm just going to flip my order because the natural log becomes positive and the sign will become negative. So, you know, it's just kind of easy to write it that way instead of having to write a negative and in front of the sign and then plus. So anyways, I just write it like that. You don't have to. All right, our y is stuck inside of a natural log. So that means we need to write this in exponential form. Okay, so e to the natural log of 2 minus the sine of x is equal to 3 minus y. Now we need to simplify this over here before we continue to get y by itself. Remember, this is always going to happen. We can decompose. This came from multiplying these two expressions. So e to the natural log of 2 is simply 2. So we've got 2e to the negative sine of x is equal to 3 minus y. There's a number of ways that you could look at this. The y is negative, so technically these two terms just kind of switch places. Y on the left and 3 minus 2e to the negative sine of x. And that's as simplified as that will go. You can't combine the 3 and the 2 because the 2 is multiplied by the e to the negative sine of x. One thing that I would always do whenever I do this is at the very end, I would either come over here to the side or somewhere and I would plug in my initial condition and I would make sure that that works. Now, a lot of times they give you 0 as an initial condition, so sometimes anyways, just check it. Why not? Check it, all right? Sine of 0 is 0. 0 has no opposite. E to the 0 is 1, so we've got 3 minus 2, which is, of course, 1. So, I mean, why not check it? You may catch just a simple sign error. You know, what if you didn't make that 2 negative? What if you accidentally had 3 plus 2e to the negative sine of x? If you plug that in, you take a quick second. I mean, that didn't take long at all. I've been talking longer than it took us to plug that in. So why not do it? Because you could catch that and be like, oh, that shouldn't have been a plus. That should have been a minus for that to work out. And you don't lose that point. Because in reality, they award the most points for the process. They don't give you a whole lot for that final explanation or final equation.